Hello, everyone. Welcome to the book club of designing data intensive application. So we have been discussing chapter 8, trouble with distributed systems. Last time we discussed about unreliable networks. This time we are going to discuss about unreliable clocks and so forth. So before we go there, let's quickly do a recap of what we discussed in the last session. Uh, so we discussed that so these days we are building more and more distributed systems and we are using cloud computing, and the expectations from those systems are they should be always online and always available. And but most of these systems use commodity hardwares which are very unreliable, and our overall goal is to make a more reliable system from these unreliable components, right? So now when we talk about unreliable components, what actually is unreliable? So in this chapter, we will mainly see three unreliable things. One is unreliable network. The second is unreliable clocks. And the third we will see is process pauses. So in the last section, we discussed unreliable network, right? That when we send a request to a service, it can fail at various places before getting a response. And so uh, we want to detect that whether our request will ever be served or it has actually failed, right? So generally we use timeouts to detect that. uh, and we have discussed various strategies of what should be the optimum timeout, right? And then in this book, we have also discussed why do these requests are not served immediately? Why does it take some time, and uh, our request can still be served? So it's good to wait for some time and not immediately time out, right? So these were the reasons for delay, network congestion, and queuing. We discussed a little bit about TCP, UDP. Then we discussed about synchronous versus asynchronous network. So all this queuing and all, we see this in asynchronous network, and internet uses asynchronous network, but we can also use synchronous networks, which are more reliable, but then the problem is they will be expensive, right? Uh, and then the last thing we discussed is latency and resource utilization, which are like inversely proportional to each other. If you want optimum utilization of your resources, you have to expect that your latency will be high, right? Because then you would have to queue your requests, and your request will be served when the resources are available. The alternate approach is that you don't use any queues, and you just either serve the request if there are available resources, or you just reject the request if there are no available resources, right? So in that case, the latency will be low, but then you will not be making optimum utilization of your resources. So hopefully this time we should be able to finish this chapter if we have enough time. Okay, so now moving on to unreliable clocks. So uh, each machine in the network, it has its own clock, right? Each node had its own clock. And the clock which is used, which is quartz crystal clock, it is not perfectly accurate in those machines, right? So now the thing is, let's say when a node is part of a system, we want to synchronize its clock. So there are two ways to do it. You can use a network time protocol, NTP, or you can use a GPS receiver to synchronize the clock of your node, right? Uh, there are two types of clocks: monotonic clock versus time of the day clock. So monotonic clocks are used to measure duration. They do not give you absolute time. They just give you duration, and they are guaranteed to be always moving forward. right? Uh, Whereas the time of the day clock, it gives you the current date and time. And as we will see later in the chapter, there could be situations where we can see that this clock is moving back in time. Okay, so let's discuss about how do we synchronize clocks, and what how can we obtain the accuracy in clock synchronization, and what could be the issues, right? So monotonic clocks, they don't need synchronization because they don't give you absolute time, right? But the time of the day clocks, because it is supposed to give you the current date and time, it has to be synced with either this network time protocol or with GPS receiver, right? So, and we have already discussed this quartz clock on your machine is not very accurate, right? So now, when you are trying to sync your node with this NTP, there could be a situation when your computer's clock is too much different from the NTP server, and your node might refuse to sync with the NTP server. Uh, Another situation which could happen is if your node is firewalled from NTP, then your node will not be synchronized with the NTP server, right? Uh, Another thing that could happen is, and yeah, the most important thing is that the accuracy of your node from NTP server is can only be as good as network delay, right? Because so let's say the NTP server says the time is 7:42 a.m., right? But now it will send that time over network to the node, and it will take few seconds, right? And so but my node will see that time is 7:42, and if that network delay is huge, then the accuracy with which I have got the time will be lower, right? So that's why it can only be as good as network delays. Then the other
Sorry, Abhishek. I have a question. We are talking about synchronization of clocks of nodes on one data center or across all data centers in different geographies.
you
So,
have to yeah, you have to sync all your nodes across all your data centers, but it may not need to like you don't need to sync everything at the same time, right? So you could have your like each node could have your different scheduling or something that it has to sync itself from this NTP server, like, and it depends on your rules. Like you could have rules that whenever a new node enters the system, it has to first sync the time before it can serve the request, or you can say that every 1 hour each node should synchronize. But yeah, you have to synchronize each of your nodes with the NTP server, and now it depends on you how you write, how the code is written, to how often synchronize it.
because my doubt is because every geography has a different time. So,
Mm-hmm.
so in that case, when let's say I have a software which is actually dependent on the current time, then if because like I'm in India and you are in US, we our time zones are different. So if you sync, is it not wrong to sync then?
No, so you will sync with UTC, right? So NTP's server will give you UTC time,
Oh,
right?
okay, okay,
And
okay.
then you can, whatever time zone you want to get, you can do the calculation from UTC, which is standard, right? So
Oh, oh, yeah. Thank you, thank you.
okay, so yeah, so here basically we are discussing that although we are saying that we can synchronize our clocks with the NTP server, but we cannot say, hey, we have synced our clock with the NTP server and we are good. There are a lot of issues which could happen during the synchronization that could lead to this unreliable clocks problem, right? And so we are discussing what those problems are. So yeah, so the the fifth point was that the NTP server itself, in some way, it could be wrong or misconfigured, right? Uh, there is this interesting situation of leap seconds, which I read in the book, and then I looked even further. So leap seconds can result in in a minute being 59 or 61 minutes long. So what exactly is leap seconds? Uh, so basically we have this universal time zone, right? And it is based on atomic clocks, and it is very accurate. The UTC which is defined, it is based on this atomic clock, and it's very accurate. Then there is actually observed solar time, which is called UT1, and it is based on the earth's rotations, and this is not like, this value can change sometimes. It is not fixed, it is irregular, because like the earth rotation could slow down in long term due to climate and geographical events, right? So in that case, so let's say we are saying that it takes 24 hours to for rotation of earth to complete, right? But over long period of time, over few years, there could be a slight change in that 24 hours, and it could take little bit more or little bit less time, right? So then this UT clock, because it is based on actual rotation, then there is a difference between UTC and UT. So this leap second is where when you sync your UTC with your UT1, and this thing is not planned, like it is not fixed. Like if you think of leap year, right? Leap year, we say it happens every 4 years, but this thing is like it based on your environment and geographical events, and it is like random, it is not fixed. So randomly this leap second is introduced, and there is this committee which will tell 6 months in advance that we have to adjust 1 second less or 1 second more in UTC. So that is called leap seconds. So because of this, when there is this adjustment that needs to be done, then for that adjustment you have to make that 1 minute to be 59 or 61 seconds long. So then the other thing is that in VMs, right? So hardware clock of the VM is virtualized. So if your VM is paused or anything, then you could see that your clock is paused, right? And then when the VM resumes, you could see your clock suddenly jumping forward. And then other issue with the clocks is that software running on user devices, right? So there you are looking at the user's clock, and we should not be relying on the user's clock, because they could have set it wrong. Like they could have intentionally set it wrong, or it could have been misconfigured. But that is something that we should be careful about, that not to rely on the user clocks. So it is it is possible to achieve high clock accuracy, right? And it is used in this high frequency trading funds that needs the clock synchronization to be within 100 milliseconds. It's the legal requirement over there, but it requires significant effort and expertise to do that. So now, like, why do we need to rely on synchronized clock? So so this clock issues, right? The issues which we discussed above, they don't happen so frequently. Like they happen rarely, but even if they happen rarely, our systems should be designed in such a way that they can actually uh, the system must be designed robustly to deal with any of these clock issues, right? The bigger problem is that if your system relies on this reliable clock, right? And if there is any issue in the reliable clock, then your system will misbehave, and but like you won't find any immediate bug or immediate issue, right? Like in the case of unreliable network, if the network is not reliable, you will not see a response. But in the cases where your clock is unreliable, you might not see an immediate something stopping or immediate bug, and it could be some latent issue, some latent bug which you figure out later that because of this issue, like your system has either corrupted data, incorrect data, incorrect anything, right? So that's why debugging and finding the issues because of unreliable clocks is like a hard problem. uh, okay, so now like let's look into the real examples in distributed system, how we can use timestamps. So one of the thing is that we can use timestamps to order events, right? So basically, uh, like one of the examples which I have done is that uh, in my distributed systems, like it will run on multiple nodes, and when I'm generating the logs, each of the log has a timestamp, right? So if I want to see the sequence, that in what sequence my events happened, I can order them by timestamp, right? But actually that's a wrong thing to do, because as we discussed that the clocks of distributed systems are not synchronized. So basically you could see that a event, although it happened before, its timestamp on that node could be little more than an event which happened later, but it happened on another node, and its timestamp was little lesser, right? So instead of these using actual timestamps to order your events, we should use logical clocks or version vectors. We have discussed about version vector in one of the last session, but basically, like you would be using this incremental number, like monotonic clock kind of thing instead of absolute time. So when your event starts, so when my log starts on first node, let's say, so I will give it a value 1 as a logical clock. Now, when the request from that node goes to another node, then I will send my previous value of this logical clock, which is 1. And now when the other node will output a log, it will increment to this value, which is 2, and then it will output that, so that I can order my logs accordingly instead of using the actual timestamps, right? So okay, so now moving to clock readings and confidence interval. So, uh, so whenever we get a clock value, right, it is only accurate up till a certain level. Uh, and even if your machine is using an atomic or GPS clock, like it will have like some amount of range of error, and that is defined by the manufacturer uh, of your device, right? But if you're syncing your clock with the NTP server, if you don't have your own atomic or GPS clock, if you are using a simple quartz clock, then your error could be because of your own drifting of your quartz clock, then the round trip delay in network from syncing from NTP server. And if there is any error in the NTP server itself, then that will also be part of your system's clock error, right? So your error will be a combination of these three things. Uh, so like the example where the nodes itself, they use their own atomic clock instead of syncing from an NTP server is Google Spanner, right? Google Spanner uses its own atomic clock, and it has its true time API, which returns this earliest and latest. So this is the time range in which we are saying that my time is accurate up till this duration. It is definitely accurate, and it lies within this range. So now So now here in this section, we will see how this Google Spanner's atomic clock is useful in synchronizing clocks for global snapshots. And before we go there, first let's see what's the issue with the global snapshot. So remember in last chapter we discussed that uh, for snapshot isolation and repeatable reads, we use monotonically increasing transaction ID, right? And we say that if a write happens later than the snapshot, then the write has greater transaction ID than the snapshot, and that write is invisible to the snapshot, because when the snapshot starts, it looks at the transaction ID and it picks only those events which have transaction ID lesser than the highest transaction ID I have seen up till now. And whenever a new transaction happen, it will have a higher transaction ID. So that will not be part of my snapshot, right? So now to do this, you have to give each of your distributed nodes an increasing transaction ID, right? So if in one of the node, your transaction ID was 13, whenever an event happened in another node, it should be given a transaction ID of 14 if the event happened later. And to do that, you have to do synchronization between different nodes, right? So that overall you always produce increasing transaction IDs, right? So what are the various ways to produce this increasing transaction ID? One way is, let's assume that your system has a totally accurate system clock, right? Then what you can do is you can generate the transaction ID based on the timestamp, right? If the timestamp is higher, then the transaction ID will be higher than previous, right? But as we have discussed, that there are a lot of issues in that. So this is not a great way to do. But now imagine if your system actually is using atomic clocks, and it can guarantee that your time is accurate to a particular error level, then you can easily solve this problem. And that's what Google Spanner does. So Google Spanner uses clock to generate the transaction ID, since it knows accurately what is the earliest and latest timestamp. So if two transactions happened and their time range don't overlap, right, then we can definitely say that one of the transaction ID happened after the another, because there is no overlap. So the one which has the higher timestamp, that happened after the one which has lower timestamp, right? And to avoid this overlap, because if there is an overlap between these two timestamps, then we don't know which happened before or which happened earlier. So to avoid the overlap, like Spanner intentionally waits for that time duration to pass, uh, and it tries to keep this duration very small. This accuracy, that this duration is very small. It is like only 7 milliseconds, and Spanner will actually wait for duration to pass before before committing or before accepting the next request. Okay, so yeah, so I think that was all in the unreliable clocks. Any questions or anything to add, or should we move to process planning?
So when it actually overlap, then what would be the resolution?
I don't know, but in the books it said that it does not allow overlap. Like if there is a overlap, then you don't know. Then you have to consider the two requests happen concurrently, because you don't know which one happened before or which one happened later.
Yeah, I think the way Spanner does it is like it makes sure that there is no overlap. That's why,
Yeah, yeah,
so it avoids that problem because you know the earliest time and the latest time, right? Like, so based on that, what it will do is, let's say a transaction, a node at N1, at node N1, if according to its own clock, it is supposed to be, it is writing a value at 100 milliseconds, right? So then what it will do is it will not expose that specific transaction outside until it is, let's say the waiting time is 10 milliseconds, right? So it'll wait up to 110 milliseconds, and then only it'll expose that particular whatever, let's say it's 100 milliseconds time, right? So that even if there is another node N2 that actually lags by maximum of 10 milliseconds, right? So even if it lags by a maximum of 10 milliseconds, if it only starts writing its value at 111, right? Like, so with that lag, that 111 minus 10 would be 101, right? So it is still actually greater than the previous, which is 100.
Yeah.
Right. So it kind of avoids that that scenario where there'll ever be an overlap by waiting out that time.
Okay, great. Okay, so now let's discuss the third issue. So we discussed unreliable network, we discussed unreliable clocks. The third issue is process pauses, right? So, so here is an interesting example. So in a single leader setup, leader must know it's a leader, right? And we have seen in various examples that to actually know it's a leader, it acquires a lease from other nodes, and it has to acquire this lease frequently. And the node which has this lease is considered as the master, right? So in such a case, when the leader is handling a request, right, you will write some codes that look something like this. So you will get the incoming request, right, and you will see that whether your lease has expired or not. If your lease has expired, then you will try to renew your lease, and then if your lease is valid, then you will process the request, right? So this is how your code will look. Now, there are two interesting problems in this code. One thing is that, so this expiry millisecond, right? If it is set by a different node, then you are comparing a two timestamps which are on different machines, because this is your machine's timestamp, and this is some different machines in timestamp. So, and because of those differences, the results might not be expected. This second problem, which relates to this process pauses problem, is, let's say if you have checked that your lease is valid, right? And now before you were about to process the request, at this point, in this line, there was a big pause because of something, like because your process paused, and now there was a pause of 5 seconds before your code started executing this line. And in that moment of 5 second pause, your lease could have actually expired, and some other node could have been master, and it was supposed to take the request. It could have taken the request, but your system will process the request acting as if it was the master, right? And in this case, you could produce some unexpected results, right? So, so like, what are the reasons of this process pauses? Why do process pauses? So one of the major issues is garbage collector. Whenever the garbage collector runs, it pauses the processes because it has to do the memory garbage cleanup, right? The second thing is when the VM gets suspended. So if your code is running on the VM and that VM gets suspended, then any process which are running, because now, like, you will not assign any CPU cycle to that VM, right? So any process which is running on that VM, it has to be paused, right? The other situation could be like when your laptop lid is closed, right? Then again, then you want your CPU should not work. So again, because your process does not has any CPU, then it will get paused. The situation when your OS thread gets switched, right? So now your CPU is being taken by another thread. So this thread's whatever state it is in, it has to be paused in that state. Uh, then there is a IO delay to load class files. So when you start a process, right? So initially it will load up all the files and it will start running. But uh, like it also lazy loads some of the files. So those files, when the process has started running, and let's say some class file was not loaded initially, that has to be loaded from IO before the process can continue and move forward. And in that moment, when the process is loading that file from IO, it has to get paused before it can proceed, right? Then another example is the case of virtual memory and page faults, right? So because that page which has to be executed no longer executes in your main memory, so it has to be brought from the hard disk and then brought it into your main memory before your process can move forward. So that will also lead to process pause. And then uh, a user could manually pause the process. Like in Unix, there is a command Control Z or a sig stop signal, which will actually pause the process, right? So these are the various reasons that this a pause, which we discussed over here, that could happen and which could result in these unexpected behavior, right?
So in this case, let's say, when we check the list is valid, let's say the list is still valid, but next second it's not going to be valid,
Yeah.
then we still go and process the request. Is that right?
Yeah. Yeah. So that's what we're saying, that if we are doing something like this in the next second, if we are processing the request, then we might do something unexpected. So we should not be doing this. Like we should be using an alternate solution rather than this, or like we should be handling this kind of scenario, because this kind of scenario will be resulting in wrong results. Okay, so yeah, okay. So in up till now we have discussed unreliable network, right? And in unreliable network we have discussed that if we want, we can have a reliable network, we can have a synchronous network, which will be more expensive, right? When we discussed unreliable clock, we discussed if we want our we can have a reliable clock. We can use our own atomic clocks, which the Google Spanner does, which will be more reliable. But again, it will be more expensive, right? Because each of your machine now has to use this expensive piece of hardware, right? Similarly, the thing which we have discussed here, that your processes get paused. If we want, we can have this response time guarantee that the process, once it executes, it will complete, it will not be paused. And there are various situations where it is highly needed, right? Like these hard real time systems, which have some actual, uh, some hardware physical component moving because of your software, like this aircraft, rockets, robots, car, right? There the software must respond within that specific time. So imagine like you have pushed the brake in your car, and the process which was actually executing the brake, it got paused or something, right? Then that delay is not acceptable in those situations, right? So in those situations, you need those hard guarantees that your system will respond within that much amount of time, right? So this providing real time system, and to move and to make these kind of real time systems, like it needs support from all the levels, hardware, software. Like basically you have to write a different OS, which is a real time OS, that allows that the process which has been scheduled, it will be guaranteed uh, a CPU allocation. Or you have to be careful that your GC should not be like your GC should not be able to pause the process. So the way to do is that your garbage collector should be more efficient, right? Because you have garbage collection is needed to reclaim the memory. So that's why, and there are some programming languages that does that, but you will restrict your dynamic memory allocation, because in case of dynamic memory allocation, you have to reclaim it. So you have to make your OS in such a way that either it does not allow this dynamic memory allocation, or it's very restricted, so that there is only very less amount of dynamic memory which the garbage collector can claim faster. So again, like as the above two things we have seen in unreliable network and in unreliable clock, providing real-time system is expensive and it does not lead to maximum resource utilization. Right? Uh, so, so in these examples we have seen, like there is one specific example of garbage collection where like this approach was mentioned, how we can limit the impact of garbage collection. So basically what we're saying is, when the garbage collection start to happen, before it is about to happen, you will be, if there is a system where you will be notified that the garbage collection is about to happen, then you can treat that node as being in down state where it is not working, and then other nodes could be serving your request while this node's garbage collection is happening. And once that garbage collection happens, now this node can behave that this node is up again, and then it can start taking the request, right? So negative impact of process pause can be mitigated uh, without this expensive real-time scheduling. GC pauses can be treated as node failures, and runtime can warn about GC happening soon, during which request should not be sent to the node, right? And these latency sensitive financial applications, they use this kind of approach. Use of garbage collection only for short-lived object and restarting the process periodically before they accumulate enough long-lived objects. So here, what you're saying is, so in the above approach, if the garbage collection is going to happen, you will say that your system is down. In this case, uh, if your garbage collection is to actually reclaim the memory, right? So if you see that the garbage collection is needed, you actually restart the process. And so when you restart the process, basically you will have this, that your node is down because now your process is not working, and also when it comes back again, like it would have reclaimed the memory, right? So that is another way we can do that. Yeah. So, okay. So now moving on to this another section of the chapter, knowledge, truth, and lies. So, up till now we have discussed various kind of problems. We cannot rely on the clock. We cannot rely on the network. The processes can pause. So actually, in a distributed system, if a node has any information, right, how do we know that information is correct? Like how does a node knows that whatever information it has, it is correct, and it's sure about this, right? So how do we do that? So in so basically, we when we make this distributed system, we state some assumptions that how our system should behave, and then we design our system based on those assumptions, right? And we will see later in this chapter like why those assumptions, why do we first make those assumptions, and why do we build a system on top of those assumptions. Um so, so like some of the assumptions that we will see is that basically truth is always defined by a majority, right? So a single node, it does not have the power to take any decision. Whatever it thinks it is based on the majority's decision. So if a single node thinks it's a master, then majority of the nodes, there should be a quorum, and majority of the nodes should say it's a master. If a single node thinks that it is alive, then like overall system should think it's alive, right? If a node itself, it thinks it is alive and I can serve the request, but it is disconnected from the entire network, and the network cannot communicate with it, then we cannot treat that node as being alive, right? So whatever the truth is, your truth will be defined by the majority, right? uh, the other thing is the leader and the lock, right? So frequently we need to do things where only one of the things is allowed to do that thing, right? Like in single leader, there is only one leader, right? If we are making if on a distributed system we are making a transaction, right? And we can say that only one of the client who acquires a shared lock, that can only execute the transaction, so that we don't to prevent the concurrent writing of the same resource, right? Or let's say there is a situation when only one username is allowed, right? So in all these situations, let's see what problem we can have if a node thinks that it is the chosen one, and it does not it has not uh, is not based on quorum. So we could produce some incorrect result. So let's take this example where there are two clients, right? And before actually modifying a piece of data, it has to acquire a log, and then it can modify the piece of data. So this client one, it goes to this log service to get the lease, and it is granted a lease, and now it is returned okay, right? So now in the meantime, before it was actually going to the right to the storage service, there was this GC pause, and the process has stopped up till this much time. In the meantime, so this was given a lease for some particular time, right? This was given, let's say, lease for 5 seconds. So in 5 seconds, it lease expired. Now, when another client, it asks for the lease after 5 seconds, it will be given the lease, right? So it will be returned and it can write to the data service, right? And now imagine your code, which we discussed about, that where you have checked whether your lease is valid or not. It executed up till this point. Now the GC paused. And now when you're going to process the request, when you're going to write the data, you will write the data, but you will see that your lease has actually expired, right? Your lease is no longer valid. So then you have actually written the data, and which is incorrect, right? You should not have written the data in this case. So how do we solve this problem? So one of the easy ways to solve this problem is using the fencing token. So what we are saying with fencing token is that whenever the lock service will return the lock, it will also give an ID, and this ID will always be increasing. So whenever the first client gets the lock, it will be given the lock with the ID 33. When the second client gets the request, uh, it will be given the lock with the token ID 34. And you can only write to the storage service if your request token ID is higher than the previous. If it is lower, then your request will be rejected. So now in this case, when the token 34 has returned to the storage service, now if this client, which has token 33, it tries to write to the storage service, the request will be rejected, because we know that it is trying to write to the storage service with the old token, right? This token is no longer valid. There has been already new token issued already, which has actually returned to the storage service. So it will reject the request which came from the old token, right? So like this is one of the approach how we could solve the problem in the code which we have seen at the top, which Leon was asking about, right? What's the way to solve this kind of problem? So this is one of the ways.
On the previous slide, Abhishek, if let's say before you write to the storage, and can the client one check the time? I mean, if it's still the list have expired or not before right?
So
Because
again, mhm.
because the garbage collection is paused, but the time on that client one system still moving forward, right?
Mhm. So what are you going to do with the time? Like, let's say you,
What like it have a list time when it get the list, the client one get a list, I get a list time, and when that would process before dry data, and we check if the list time have expired yet.
so you are going to write a line of code, right? That if it is not expired, then execute something. So let's say after this you have again written that line of code, whether your lease is valid or not. Once you have written that line, that was satisfied, and after it was actually going to process the request, before that, let's say again GC pause happened or something happened, right?
Yeah.
So how will you ensure that? So okay. Okay, yeah. Moving on to one of the other issues with this distributed system is Byzantine faults. So, in the above scenarios, in the above situations, we have seen that the system, uh, it is like not working, like it has, because of some issue, it is not able to respond, right? But it is not intentionally sending any false information, right? It is intentionally trying to tell whatever the honest state the node is in, right? But uh, there could be situations where this assumption might not be true, and there could be nodes which are actually trying to deceive intentionally, or they're trying to send some wrong information, right? uh, and in that situation, if your system is based on solving these kind of problems as well, where the assumption is that your nodes could actually lie, then it becomes much harder to solve all these problems, right? But actually there are some systems which are based on that. So so the problem of reaching consensus in this untrusting environment is known as Byzantine generals problem. And what are the use cases of these problems? Like one of the example is, in aerospace, right? The data in computers memory or CPU register, it can get corrupted by the radiations. And there, so actually, although your system is not intentionally lying, but actually it is a lie, right? Because the value which you stored was something, but now it has, because of the radiation or something, it has changed, right? So in this case, like generally, like in non aerospace environments or something, right? What we do is we make this system fail, right? Initially, at the very starting of this chapter, we have discussed that in single node machines, if something wrong is going to happen, we just make it completely fail, right? But in these kind of scenarios, aerospace kind of scenarios, you don't want your system to fail, because like you are already on limited resources and all, so your system should have this fail proof mechanism. So in these cases, your system should be able to tolerate this Byzantine faults. uh, and the another, which is very common scenario which we all know about, is this peer-to-peer network, right? When there are multiple participating organizations and there is no, like, there is one source of truth, your network is based on peer-to-peer, and the example is Bitcoin and blockchain. So there, one of the peer could be intentionally sending the wrong information. uh, so Byzantine fault tolerant system are quite complicated. So generally so in this book, in designing data intensive application, the systems which we will discuss are not Byzantine fault tolerant, because in most situations your node lives in your data center and your data center is in your control. So all nodes are controlled by your organization and they can be trusted, right? But again, like there are some other scenarios, like if anyone knows about edge computing, right? So in edge computing, this is a new kind of cloud servicing offer where the a mini data center in the form of few machines or few rack is actually shipped to the customer, and it lives on the customer's location, and and there it is serving the request from the customer location, so that the latencies where the nodes are living in your data center are not high, because the request has to come to your data center. So if a customer says that my work is very latency sensitive, then you like there is this scenario of edge computing where you ship the nodes, your data center, that mini data center to the customer. So in that case, your machines are not in your control because you have shipped those machines to the customer, right? So I was thinking like that could be one of the situations where this assumption that your nodes live in your data center and they could be relied on, that assumption is broken again, right? Uh, and uh, and then the other scenario is this web applications, where a user could be giving any malicious input or wrong input, right? And in those cases, you have to do the validations because the client, the user could be sending the wrong information. But actually, I think that is something which is the application level faults. And the above, which we have discussed, are like overall your distributed system, how it is operating when it is talking to different nodes, right? And this was talking about the nodes in your system, whereas this uh, client, it is like an external component. So whenever you're dealing with any external third party component, in this case, which is a web application which is being accessed by client, then definitely you have to think about that you could be intentionally, that person could be sending the wrong information, and you have to validate that information before actually serving it, right? So so then this weak forms of lying, right? So uh, even if you say that your system is honest, even if you say that your nodes are in your data center, there could be some weak forms of lying, and it could be worthwhile protecting your system from those kind of lying. Like one of the like few of the examples is so your message, it became corrupted, right? Because the network packets got corrupted, and although UDP and TCP takes care of it by using the checksums and taking care that the network packet is not corrupted, but still this network packet in some situations could evade that detection and it could still be corrupted, right? So then the approach we can take is that you use checksum at the application level. So at the application protocol also you are using the checksum, so that you can totally validate that your message was correct. Then there could be some software bugs. Because of some software bugs, the data would not be as expected, right? And that could like actually that is some form of lying to you because the data was not what you expected. There could be some misconfiguration. Then we have discussed this web applications example. And then similarly, in case of unreliable clocks, this NTP server, right, or NTP machines could have wrong clocks. So the way you should synchronize your clocks with NTP server is, instead of synchronizing from one NTP server, you will be sending a request to multiple NTP servers, and based on the kind of quorum of what you see the time from various NTP server, you will take one of those which satisfy the quorum, so that even if your NTP server is giving you wrong information about the time, that is ignored, right? If one of the NTP server is wrong, because your decision of what the timestamp is will be based on the code, right? Okay, so talking about, so so remember above we talked about that our systems will be based on a system model and some assumptions, and we will be defining our distributed algorithms based on those assumptions, right? So what are those various kind of assumptions that we can have in this system? So in case of the timing, right, there could be three kinds of assumptions that a system has. One of the assumption is that you have a very a very expensive hardware, where we are saying that our network will be synchronous, right? And we will have bounded network delays, bounded process pause, bounded clock error, right? We have that expensive kind of hardware, expensive setup. So in this synchronized model, to emphasize, it does not mean that your network delay is zero, or your process pause is zero, or your error in clock is zero. It just means that there is a fixed bounded, there is a fixed upper limit of what that error could be, right? So that is one kind of system model that you could build your algorithms on, right? Another system model could be, you are saying that your system is partially sync, right? So what we're saying with partially sync is that in most of the situations, my system will be behaving as synchronous, but in some situations, uh, these network delays, process pauses, and clock errors could exceed the bound, and that bound could be like very high, and we don't know what that upper bound is, right? And most of the actual real time systems are based on this assumption of partially sync model, where we are saying that most of the time uh, our system is well behaved, but you have to take care of some situations where it might not be well behaved, right? The third situation is extremity of this unbehaved manner, where we are saying that our system is totally asynchronous, and an algorithm is not allowed to make any timing assumptions, like, and in fact you are not allowed to have a clock because you cannot make any assumptions about time. And so that is one kind of system as well. This kind of system will be very hard to design, and it will be very restrictive, because like you are not having any kind of guarantees in the system, like you're not making any kind of assumption that something will happen correctly, right? So these were the three kind of assumptions that you could have related to timing. Most of the systems that we will discuss are based on this second assumption. The Then there are three kind of assumptions related to system model, right? Sorry, there are three kind of assumptions related to node failures, that what kind of node failures could happen. So one kind of assumption is crash stop faults. What does it mean is that whenever your node fails, it will crash and it will never recover. It is gone for forever. So you have to build your algorithms assuming in such a way that your node is crashed and now it will never recover. The second kind of system models which you can define is that your nodes will recover after fault. So your nodes in the system can crash anytime, but after some time they will get recovered, and that some time is some unbounded time which you are not sure about. These machines will have a non-volatile memory, like some storage hard disk or something, and some volatile memory. So when the system crashes and it recovers from the faults, the data stored in your volatile memory will get lost, but the data stored in your non-volatile memory will not get lost. So now you can build your system on this assumption, this kind of assumptions, that this crash recovery fault where your nodes can fail, they will recover, your non-volatile data will still be there, your volatile data will get lost. And the third, again, this extreme kind of system is Byzantine fault, where the nodes may be alive, may be dead. If they are alive, we don't know what they are saying. The information they are saying, it could be deceptive, it could be wrong, right? So again, here we will be, the most of the systems we will be talking about the second kind of systems where the nodes fail and they are recovered, right? So so most of this systems are based on this second assumption of timing and second assumptions of node failure, right? So now, based on these assumptions, once you have defined a system model, then you will define an algorithm for your distributed system, right? So how do you actually tell that the algorithm which you have defined for this distributed system, it is actually correct, right? So what we will do is we will define some properties that your algorithm should fulfill these properties. And if we can say that for these system model assumptions, if this algorithm is able to fulfill these properties, then we can say that this algorithm is correct, right? Like an example of when we were generating fencing token. So whatever algorithm we have defined, we can say that algorithm should have these properties, that uh, it should be unique. So unique in the sense that no two requests will get same fencing token. The fencing token should have monotonic sequence, means if a request that happened later, it should get a value of fencing token which is higher than before. And availability, that if a node is asking for a fencing token, it eventually after some time it actually gets a fencing token. So if we can say that the distributed system which generates the fencing token, the algorithm, if it follows these three properties, then we can say that our fencing token generation algorithm is correct, right? So this is how we can define the correctness of the algorithm based on the property that it should fulfill those properties. Uh, so again, like formally the definition, an algorithm is correct in system model. So again, your algorithm will be correct for that particular system model. First, you are defining the system, that this is my system model, and then your algorithm is correct in that system model if it always satisfies its properties in all situations of that system model, right? So why do we need this? If all node crash, all network delays suddenly become infinite, no algorithm will be able to get anything else. So this we will see more in this section, mapping system models to real world. But basically what we're saying here is that we have to build an algorithm on some assumptions, on some particular system model, right? If you just directly go to the extreme situations where everything can fail, where the network is unreliable, then it will be really hard to build your system based on those extreme situations. So basically, when you start building something, you build something on some constraints, some defined constraints, and some defined assumptions, and then you try to build your algorithm on those assumptions. Uh, so uh, I think someone has their mic on. Can they turn it off, please? If they're not going to speak something, or if okay. So so two more new terms: safety and liveliness. What is safety and what is liveliness? So the above which we discussed these three properties, right? Uniqueness, monotonic sequence, and availability. So here, uniqueness and monotonic sequence, these are safety properties, and availability is a liveliness property. So by safety, we are saying that in our algorithm, nothing bad will happen, right? And by liveliness, we are saying that whatever algorithms we are building on our distributed system, those algorithms are in a way that eventually something good will happen. It will never just eventually after some time something will happen. Uh, for distributed systems, it is common to require safety properties always hold true in all possible situations of system model, right? Um, and but with liveliness, we can make some caveats. So with liveliness, we can say that you will get a response in your request only if majority of nodes are not dead. But if all of your nodes are dead in a worst situation, then you can say that yeah, my system will not be live, will not be available, right? So I think the example is that uh, like whenever we are opting for any uh, in this any cloud computing service or storage service, we are those services are definitely giving us this safety guarantees, right? That we will not see incorrect data or something. But with availability, they have some value, that 99.99, right? Which is a liveliness property. So with that, they are saying that yes, your system will be mostly available, but in some worst situation, in some worst cases, let's say our entire data center rack got disconnected or something, in those situations for some time your system could be unavailable, right? So that's what we're saying, that in distributed system, safety should be always ensured. We should try to build algorithms which are always safe, but with liveliness, we can make some caveats. Right? Uh, Now, mapping these systems to real world. So, whatever assumptions we have made above, right? Whatever system model assumptions we have made, in actual real world, you might see that those assumptions are not true. And those, your worst fears or your worst things which you have thought that these are very, very rare situations, that could also actually happen in the real world situations, right? So, but now the problem is, will you build your system based on all those worst assumptions? Will you start making your system based on all those worst case scenarios? And it's actually hard to build a system on those worst case scenarios. So basically, like it's like basically breaking down your problem into simpler problems, for solving those simpler problems, and then finding the solution of those edge cases and harder problems, right? So similarly, we are saying in this case that initially you will build your system on a system model on an assumption that we are saying that eventually the nodes will recover and all those things, right? And eventually, once you have those constraints, then it's easier for you to build a system. Once you have built the system on those constraints, once it satisfies those things, now you can actually work on those other rare case scenarios, other rare case problems, and solve those. So that's what we're saying here, that when we implement real distributed systems, it becomes clear that the system model is a simplified abstraction of reality, and it might not always hold true. So so basically, like the algorithms which we have discussed in the crash recovery model, they assume that your storage is stable, right? And once your node recovers again, you will have your data, right? And many of the quorum algorithms, they rely that whatever data was with the node, it will remember that information. But in theoretically, uh, these situations might not happen, and a node might actually completely fail. Your hard disk might completely burn out or something, and your node might never actually recover, right? So basically, theoretically, we can say that some things will not happen. However, in real situations, those rare things can also happen. But it does not mean that these theoretical abstract system models are worthless. They help you manage the complexity of the real system, and they help you basically constrain the set of faults that you have to manage and you have to reason about, so that you can solve and understand the problems systematically. And once you have built those system based on those theoretical assumptions, then now you can further improve your systems. And then you also need to do theoretical and empirical testing to actually see that your system is working correctly in all the situations. Yeah, I think that was it. Most of this chapter was a lot of theoretical, but yeah, I found this really interesting. That yeah, I mean, why? So, like, I remember when working with real world problems, like sometimes when you're thinking about the solutions, you are thinking about what if this also fails, and you start taking about these worst case scenarios. And then actually I have seen that it becomes really hard to solve anything and to actually move forward. So in that case, like, it's really important to understand that first you define a system model, that these are the assumptions I'm taking. I'll be making my algorithms based on these assumptions, so that actually I can solve some problem first, and then actually improving your systems later for these rare kind of scenarios. So that's it from my side. If anyone has anything else to add, please continue. Else I'll stop recording.